We never got around to it. So
the problem's still there.
the problem's still there. So everybody's, by now, this should be our favorite equation up there, the Einstein field equation. And we all know the history. Most of us know the history. How do we point? Hockey stick, that's right.
And you also need to put this on, I think.
Keep it on the microphone, please. Oh, microphone. Yeah. Yes. I need my time back. We will not talk about the problem of time. That's a big one. All right. Should this work? Can everybody hear me? Okay. All right, so let's begin with this famous equation. This is the classical Einstein equation. And if we follow the prescription, so the first thing I want to talk about is a UV problem. So the cosmological constant problem that I'm going to talk about has both a UV part and an infrared part, okay? High energy and low energy. Small distance scale, large distance scale. So a way to understand what this UV problem is, and now the UV problem we're going to speak about, is in the context of perturbative quantum field theory. In other words, the type of quantum mechanics, relativistic quantum mechanics, that we know works. Okay? So if we turn to page 150-something of Burrell and Davies, and we are informed how to use perturbative quantum field theory to calculate the vacuum expectation value of the energy momentum tensor. So if you go through that calculation, we find that this is actually the bare cosmological constant, actually gets corrected, or sorry, the VEV of the energy momentum tensor corrects the this bare cosmological constant to include higher derivative curvature terms. And what's important here is that after renormalization, after renormalizing infinities, these parameters cannot be determined by the field theoretic prescription. It's the same issue why we can't calculate the bare mass of the electron in quantum field theory. So this is one issue that if you want to try to solve the cosmological constant problem using field theory, you have to now determine what these parameters are so as to tune lambda to be the effective cosmological constant, which includes the bare cosmological constant, and these corrections to be 0. All right, so let's look at that in let's look at why that's happening. Why that's happening is because if we now look at an individual quantum field, for example, let's take an electron, I'm sorry, a spinor field. Well, that's a bad example. Let's take a scalar field or a gauge field. What you find is that all of the free oscillator states have a 0-point energy that will couple to gravity. I will show you that in a second, but the important point is that when I integrate this 0 mode, the frequency up to momentum up to some cutoff, which is the cutoff of the effective field theory in mind, you're going to get this cutoff squared that will contribute, because this is a constant, a 0-point energy, that will basically have huge contributions to the cosmological constant. Or imagine that you provide me a mechanism that fixes that part. If you have some cosmological phase transition in the early universe, it could come back to haunt you, and here you can have another contribution just from spontaneous symmetry breaking. And in fact, this was a nice critique that Nima Akani Hamed had for modified theories of gravity that actually tried to solve the cosmological constant problem. This could come back. You have to check to see that this you also relax lambda based on this. These are degravitated models. Let's look a little bit further. If you say, I think that's all crap, then I'll turn on the Lamb shift, which has been observed, right, for hydrogen. And this is a vacuum bubble here of an electron, a virtual electron pair, which is a vacuum bubble. Thanks to John Moffat for pointing this out to me, the man that taught me the cosmological constant problem. And what we see here is that Polchinski showed that if you actually have a graviton here and you remove this graviton, you spoil the equivalence principle by 6 orders of magnitude. So you can't mess with gravity too much when it comes to coupling to matter for these vacuum bubbles, which has been observed. So what you're informed to do is to try, because of the equivalence principle, to do the same thing for root g times lambda, where lambda now is a vacuum bubble, And if I expand root G, I'll pick up higher ordered graviton diagrams with more graviton legs. But if you do that and you believe this, then you're going to get, this is where you get these huge contributions to lambda. So what are you to do? Well, what are you to do? Yes?
Just it depends on the regularization. If you use dimensional regularization, you find 0 for the tensor. I'm not saying this one. If you take a regularization which is Lorentz covariant, like dimensional regularization, this diagram.
Which one?
The tadpole.
This one here?
Yeah. Radiates to 0.
No, but you can't normal order the graviton legs.
No, but I take dimensional. I'm just saying. It really depends on. If you take a Lorentz covariant. I'm not saying it's a solution, but it's often not mentioned.
This is not correct.
Okay, let's not argue about it. It is, but
Anything said about the rest.
So that's not true for massive field, isn't it? For
dimensional regularization doesn't have lambda.
even for massive fields, I don't think that's true. For massive fields, you do get.
I mean, all I'm saying is that.
You mean minimal subtraction plus? So it's not only dimensional regularization, but minimal subtraction.
Yes, Lee?
Yes, you can still decouple the graviton in unimodular gravity. Decouple the graviton from this trace theory momentum tensor in unimodular gravity. That is another reason why this argument is not correct.
This argument is not correct.
Yeah.
And that fixes the equivalence principle?
Yes.
Okay. So then we're done. We've solved the cosmological constant problem.
It's a different problem. It becomes the fifth in your list, because in unimodular gravity, you eliminate, you decouple the gravity from the vacuum fluctuation.
Right.
But the cost of that is you get a constant of integration.
Right.
And now the problem is just why is the value of that constant of integration for this particular universe what it happens to be observed?
Okay.
It's the same problem.
Well, no, it's a different problem because there's no longer a problem. There's no longer a problem with vacuum fluctuations.
Okay.
You can show in the quantum mechanics.
So I'm going to show a different perspective of how people are thinking about this now. So a big part, one of the problems with that argument as well, too, is that those calculations were done using Minkowski space. They were done in flat space, okay? So you're evaluating a correction to the cosmological constant using flat space. And so there is a school of thought that says we need to do it self-consistently. We need to evaluate the cosmological constant problem at least in space-times with a cosmological constant. So you have to do quantum field theory now in de Sitter space. And this is the philosophy of people like Richard Woodard, and most recently Polyakov, and also the philosophy of, so I'll say a few more about, from Robert Brandenburg and Slava Mukhanov and Raul Abramo. And then that idea is that, that idea is simply to say, to do it consistently, calculate in de Sitter space, and, that should be and one discovers that acceleration can lead to an instability. In other words, when you do this calculation, the fact that the space-time is accelerating, there's a back reaction onto the quantum correction that negates the cosmological constant and drives it to 0. So to give you sort of a, so there are some ideas here, which is to use quantum gravitational back reaction. Again, what I mean by that is you look at 2 loop effects, okay? And the idea is that those 2 loop effects will come back to negate the cosmological constant coming from the 1 loop effects. Of course, that stuff is very nasty, and you read any Woodard paper, you just want to pull your hair out, or his hair out. And
Somebody has done that.
it's all love, Richard. All right, and of course, there are some problems with this. One problem with this is, of course, that you do a perturbative calculation, but the regime where this growth of the effective cosmological constant becomes large is in a non-perturbative regime. So motivated by that, if we look at quantum back reaction of the energy momentum tensor, classically, Raul, Robert, and Slava have shown, actually, that you can get, under some assumptions, back reaction to cancel lambda. So this is also in the spirit of some work that, that Rocky Kolb and others have been pursuing to use that to explain late-time acceleration. Yes?
In that work, they use dimensional regularization, if I'm not wrong.
Yes.
In the first one.
From my memory, yeah, but I'm not an expert at it.
Do you think that one should throw away this pure vacuum then? That should be the correct.
It's a good question, but let's say that for the discussion section. No, it's a great question. I mean, I think what you guys are saying is, it'd be good to look into that, but yeah. Yeah. We can discuss this. Okay, let's do that at the end of the talks. I'll bring that back.
Okay, good. Dimensional regularization only works for logarithmic cutoff. This is well known. It is blind to anything higher than.
Okay. Let's get back to this. Let's get back to this. I'm also the chair, so. And I have the stick. Behave yourself. And there was a very crazy idea which sort of brought matter into the picture, saying that, well, if you have fermionic matter in the picture and consider the graviton coupling to that, that will make the fermions condense, and that will eat up the vacuum energy that you thought would contribute to the large vacuum energy. And so John and I tried to publish this paper, but we got no love, as the saying goes. So just to give you sort of an illustration of how many of these mechanisms work, let's consider an old idea by Dolgoff, and then there's an improved version by Larry Ford. Now, this effective action is actually, if you look at Larry Ford's original paper, it is motivated. It's an effective theory that captures the two-loop graviton effect, okay, some diagrams. So Larry shows that, you know, this extra term does capture these graviton effects. So the way this model works is that if you study this in an accelerating space-time, if you now go you self-consistently solve, okay, the Einstein equation, or there's actually an R here as well. There's also an R, okay? So this is gravity plus the scalar sector and this what seems to be conformal coupling, but it's not quite conformal coupling. Now, if you go ahead and solve the field equations, you find an early time behavior where this field appears to be unstable. Well, this just basically reflects the instability and the infrared mode of an inflaton field, quantum perturbation and inflation. But what you find is that at a late time, this term starts taking over, and the scale factor actually starts growing as if it's in a regular FRW radiation-dominated universe, for example. And the effective energy momentum tensor now scales with, as lambda naught. But this gets subtracted from the bare lambda naught. So you start off with a bare lambda naught, which is assumed to be the Hubble parameter doing this accelerated thing, and this gets back reacted, okay? And you're led to this thing. So that's the basic feature. And that captures some of the quantum mechanics that Woodard, and it'll be interesting to see if that reflects the kind of stuff that Robert did with the back reaction and the momentum tensor. Yeah.
I think I missed something, because the description up to the fourth line is classical, right?
Yeah, so basically what's really going on is this. Okay, so this is lambda effective. At first, this thing is 0. You turn on, right, you set that to be 0 at the beginning of inflation, let's say. It's not inflation, you're just looking at the Sitter space, lambda. All right, and what you find is that at a later time, this actually starts scaling like lambda, but also exactly right in the regime where now the scale factor just becomes FRW-like.
So I don't understand, the expectation value of the energy momentum tensor is not conserved in this process?
No, it's not conserved. That's fine. Okay. So let me say a few words about the infrared problem, which is, I think, a more serious problem. So that's just in the ultraviolet problem, perturbative quantum field theory. Well, the infrared problem is that the observation that the universe is accelerating. And either, okay, the source of this acceleration is a time-dependent thing, fluid. In that case, it's not a cosmological constant. Then there's no need to worry. We just got to explain why lambda is 0 and what this thing is, okay? Or Occam's razor, or it is actually a it is a cosmological constant where the vacuum energy is 0.002 electron volt to the 4th power. And that's an infrared number, okay? How infrared is it? Well, the most infrared thing we know of in the universe, and now I'm going to talk about a quantum gravity dream. So even if you find a mechanism to kill lambda via, let's say, the kind of stuff with backreaction, okay, you now have to explain now why some residual is left over, and that's what we call the infrared problem, okay? Or even if you can tell me why this, lambda is this, okay, by summing up everything, let's say you had some theory that can do that, you have to tell me what the dark energy is. So either way you look at it, it's a problem or an opportunity. So what's a way around all these problems? So I'll give you a thought experiment to think about, not that I have a solution, okay? So let's say we had a theory of quantum gravity. I just want to put this in context of this workshop, okay? So we're thinking about quantum gravity and experiment. So what if this cosmological constant problem is a quantum gravity problem? I'm not saying it is or it isn't, okay? It's definitely a problem in perturbative quantum gravity. But what if we had a quantum gravity theory? So what this theory tells us is that the cosmological constant, so the caveat here is that whatever your quantum gravity theory is, it better get back to perturbative quantum gravity. So that's my order. So if you don't care whether or not to get back to connect your theory to the perturbative connection of effective quantum gravity, a la John Donahue, okay? If you have that connection, then an opportunity would be to figure out how your theory, your quantum gravity theory, only couples to the vacuum bubbles perturbatively. But in the semi-classical limit of your quantum gravity theory, when the gravitational field is semi-classical, so you have flux, for example, that whatever that is, it excludes graviton coupling to matter quantum fields. All right, this is a weird idea. Okay, then we can implement the backreaction mechanism a la Woodard and Brandenburger, and you solve the cosmological constant problem in both regimes. Okay, so with this prescription, then the test of your theory, you see your theory will now potentially predict something. Then you can ask, how does it solve the infrared problem? Then you can ask of your theory, how would I solve that? Because you didn't solve that. And so a hint, which is very speculative, is that this vacuum energy has a very interesting thing, scaling, that it is the ratio of the electroweak scale divided by the Planck mass. So, and that's nothing more than the mass of the neutrino. So the neutrino is very special, especially the sterile neutrino, because it couples to nothing but itself in gravity. Okay, so that, again, this is a wild speculative idea, but it's just to leave a wild speculative idea as food for thought or dessert. Okay, stop. Wait a minute. I'm the one that's supposed to be saying that.
You are.
Okay.
Just a reflection of your...
Okay, on that note, we'll get the first speaker. Thank you. Oh, yeah. Mike Dupuis, is that correct? Okay. All right, we're going to put this up. How do we put this up? Okay.
so I don't need the.
Yeah, I want to put
Please.
You want to use blackboard?
Yeah, I'm doing a blackboard.
Use that.
What do I? Oh, okay. 10 seconds. Okay. Okay, so is it loud enough? Yeah. So first, thanks to the organizer for this opportunity to talk here. So I want to talk about some results of a project done in collaboration with Florian Girelli. Well, the idea is to define loop quantum. So I'm going to go back to loop quantum gravity observables for hyperbolic geometry. So our first motivation was to take seriously all the proposal by Lis Molin and Carlo Rovelli to incorporate a non-vanishing cosmological constant into the loop quantum gravity framework. So the idea is to use, instead of the SU2 gauge group, to use a quantum group. So here I'm going to work with UQ SU2, which is so the quantum deformed universal enveloping algebra of SU2. And Q, of course, is going to be related to my cosmological constant. And for some technical reason, I'm just going to consider Q real. Okay. So this idea is also motivated by the Turay-Viro model, which is a spin-foam model for 3D gravity with a cosmological constant, and which is based on this quantum group. So first, in the first part, I'm going to give you some basic ingredients of loop quantum gravity that I'm going to use in the following. Then I want to focus on a simple example. So I'm going to consider the 3D case, loop quantum gravity, and define the angle operator in this context. And what I want to show you is that from this operator, we can already see that we are quantizing some Euclidean geometry. So then I want to generalize this operator in the case of the quantum group case, so for UQ SU2. And what I want to show you is that this operator is now going to characterize some hyperbolic geometry. And then in the last part, if I have some time, I just want to give you what are the important tools we use to define. So some technical details, what we use to define this operator, which can then be used in the 4D case, to define some operators in the 4D case. Oops. Okay, so let's start. So first, loop quantum gravity. So it has been established as a non-perturbative and background independent quantization of general relativity through a canonical scheme. So the starting point of loop quantum gravity is a smeared algebra, the so-called holonomy flux algebra, associated with graphs embedded in my 3D manifold. So now I'm considering graphs. I'm doing a very simple one, and to each link of this graph, I have a couple of variables, so an holonomy and a flux. Voilà. So the holonomy is a SU2 group element, and the flux can be seen as a SU2 Lie algebra element. Okay, so then at the quantum level, the building block of the theory are the spin network states. So a spin network state, they form a basis of my kinematical Hilbert space of loop quantum gravity, and they are defined by a graph plus a coloring. So the coloring is now given by irreducible representation of SU2 and intertwiner, which are invariant vector in the tensor product of all irreducible representation associated to the ingoing or outgoing edge of my vertex. So I'm going to note AV. Okay, so what is the important result of loop quantum gravity is that now our space is discrete. Okay, so how can we see that? To see that, we compute some geometric observables, so the area operator or the volume operator, and both operators are diagonalized by the spin network state, and their eigenvalues are discrete. So, in fact, you can see a spin network state as a quantum excitation of space, where now, so I need some, an edge is going to carry quanta of area, okay, and a vertex is going to carry a quanta of volume. So it's, well, I'm not going to draw it. Okay, so now, so this is a main result of loop quantum gravity, and it's important for phenomenology. So now the question I want to ask is, first, if we define operator using a quantum group, then first can we relate this operator to some cosmological constant, and do we still have this discrete property of space? Okay, so first I'm going to still work in the standard loop quantum gravity, but I'm going to take a simple case that is 3D gravity, which is a topological theory, so we know exactly how to quantize it. And I'm going to define some operator. So now, in the canonical framework, what do I have? My space is a 2D surface, and for simplification, I'm going to consider that the surface is triangulated. That means that now my spin network are dual to a triangulation, and in particular, each vertex is going to be dual to a triangle. So let me label this triangle. So A, B, C. So I'm going to label this edge A, this edge B, this edge C. And so as I said, an important variable to associate to this graph are the flux variables. So to each edge of my graph, now I have XB flux, XC, and XA. And in fact, the SU2 invariance of this vertex is going to be imposed through the closure constraint on this flux variable. So where now alpha is A, B, C. Okay. So you see that it's natural to see the flux variable are 3 vectors describing my triangle. Okay, so I'm going now to say that XB is going to describe my edge B and etc. So and now, so that means that I can interpret this closure constraint just as a constraint, a closure of my triangle. Okay, so and you see also that from this flux variable, this 3 vector, I can get all the information about the intrinsic geometry of my triangle. That means that length of a given edge is going to be given by the norm of the flux variable associated. And if I want to define an angle, so theta A, the cosine of this angle is simply given by the XB scalar XC normalized with LB LC. Okay, so now at the quantum level, we can also define observables to describe this intrinsic geometry. And it's easily defined on what I call the spin network state. So now I'm going to consider a simple spin network. So label with JB now the edges are labeled by my quantum number and by an intertwiner. And I'm going to quantize my flux variable as roughly SU2 generators, okay? So now to define the length operator, or more precisely the square of the length operator, is simply given, for example, for the edge A, it's simply given by XA squared. And the action of this operator on my spin network is diagonal, and it's simply the SU2 Casimir, so I just get J. And I can also define the scalar product operator of two different flux variable on different edges. So this operator is also going to act on my spin network in a very simple way. It's just acting as a grasping operator. So in fact, it's just adding a spin 1. So you get this. We also have some proportionality coefficient. And so if I compute this, I get a very well-known object from SU2 recoupling theory. It's just a 6G symbol. And it's proportional to this state. Okay. So now, in fact, if I use the normalization of this, if I normalize this operator, what I get is just what I'm going to call the cosine operator, so for the angle A. And the action of this operator on my spin network can be computed explicitly using developing this well-known object, and we just get that it's equal to JB plus 1 and divided by square root. So B and so now how can we interpret this this equation? In fact, if you remember that the length operator, the length is quantized as J plus 1. In fact, you can see that this equation comes from the quantization of this well-known classical equation, which says that cosine of theta is equal to LB squared plus LC squared minus LA squared divided by 2LB LC. And this is just the usual cosine law. So in fact, what I just want to say is that you see that this operator characterizes some Euclidean geometry, because this is the cosine law for an Euclidean triangle. So now what happens if instead of considering SU2 as a gauge group, I consider UQ SU2? So that means that now I'm going to work with intertwiner defined with UQ SU2 gauge group. So the irreducible representation associated to my edges are now irreducible representation of UQ SU2, and my intertwiner is a UQ SU2 intertwiner. So I'm going to put a small q to say that it's a q-deform spin network, and I can generalize this operator. So what is important in this operator is, in fact, that the SU2 generator, the component of my SU2 generator, in fact, form what I call a tensor operator of rank 1. So T1. That means this object is transforming is transforming as a vector, in fact, under the action of SU2. And in fact, what I call here the scalar product is just the fact that from two vectors, so two vector tensor, two vector operator, here I'm doing a scalar operator, which is invariant under SU2. So now I want to do the same thing for UQ SU2. That means I want to build some invariant object under the action of UQ SU2. So for this, I'm going to start from tensor operator of rank 1, that is, which transforms as a vector under UQ-SU2. So now it's not just the component of the SUQ2 generator, but it's a function of this, much more complicated of this generator. And from this, so if to each leg of my intertwiner, I'm associating a tensor 1 operator, and I look at the action on this Q-deformed intertwiner. So this is well defined. It's invariant under the global action of UQ-SU2. And this action is in fact the same as this one, instead of that now we have a 6G symbol Q-deformed. So we get more or less the same result. So now how can we interpret this equation? In fact, once again, using an appropriate normalization of my vector. So in fact, the normalization of my vector is now a function of J plus 1/2. So in fact, I'm going to interpret this as a quantized length. And then this equation just become, I'm going on the other. So my equation TB scalar CT acting on my Q-deformed spin network, when using the right normalization, is in fact what I'm going to call the cosine, once again, the cosine operator acting on my Q-deformed spin network. And from this, what I get is a function in terms of hyperbolic function. So I'm going to give you what is lambda. That's way too. So JA plus 1/2 lambda plus some sine B 1/2 lambda divided by the normalization of my tensor. So now lambda is related to Q, of course, it's ln of Q. And in the 3D case, I can say that Q is equal to exponential of LP square root of my cosmological constant, where here I consider a positive cosmological constant. So in fact, you can, so now let's come back to this equation. So I forgot, yeah, so it's the action on this. Let's come back to this equation. In fact, you can see this equation as a quantization now of what is called hyperbolic cosine law, which is given in terms of, so I recall you that we interpret this as a quantized length. So which is just given, LB, where R is now my hyperbolic radius. So here R will be the cosmological constant radius in this case. Where here, so what I'm considering now, it's a hyperbolic triangle. So let's continue. And so this relation gives me the relation between this angle and the length LA, LB. So in fact, you can see that now the relation I obtain acting with this operator on a Q-deformed intertwiner is a quantization of a hyperbolic law. So what does it mean? Yeah, I'm done. I'm concluding. It's just that this is the first sign that using a quantum group, so first, using a quantum group, the quantum deformation can be related to the cosmological constant. And then using a quantum group, you can get some quantization of hyperbolic geometry. And what is also important is that the discretized aspect of the theory of loop quantum gravity is still here. And I think I don't have, so yeah, just let me 2 minutes, 1 minute more. It's just to say that the important tools that we are using here are the tensor operator, and using this, they are really the building block to build observable for an intertwiner for any kind of group. And then using this tool, we can then compute the volume or area operator for the 4D case, for example. So this was just a simple example. Okay, thanks.
Excuse me, that Q is the deformation parameter.
Yeah.
LP is the plane scale.
Yeah, sorry, I forgot to say.
If you expand this, the expansion gives you 1 plus L plane divided the whole radius, basically. I mean, if you expand it.
Yeah.
Okay. Thank you.
Yeah.
Yeah. So the work that we did originally that you cited was actually with Seth Major, not with Carlo. And so I want to take the opportunity that Seth has also worked on an area operator. Is there a relationship between an angle operator, between his angle operator and your angle operator?
Yeah, I know that Seth is also working on Seth, here. Sorry. So I think you're working with so first you were working with a 3D diagonal angle, no?
Right.
And then, yeah, I guess the way to define the operator is not really different. What I wanted to show is that from this operator, you can get an equation which characterizes, in fact, some hyperbolic geometry. But then the definition of but yeah, and also the key point here is that to define because we define invariant operator, so what we call for the intertwiner space. So the key point to define this operator are really the tensor operator, and this I think it's new in the loop quantum gravity context, because so it's well known in quantum mechanics, but in the loop quantum gravity context, I think it hasn't been really used. And in fact, you can see that all the recent work about the spinor formalism or the UN formalism can be really re-expressed in terms of tensor operator variable. So in fact, it's really a way to generalize a lot of and to define a criteria. Yeah. So.
Could you comment on the change from the J plus 1 version of Casimir to the J plus 1/2?
Okay, yeah, so in fact, in loop quantum gravity, usually we are using L square is equal to J plus 1. So then the square root will be, if for large J, it will be more. So we get the same. In fact, it's just a kind of reordering ambiguity. It's not, in fact, it's the same.
Was it necessary to do for this construction, or is it just?
It's just that for this construction, it's a natural length operator which upper, and it's also nice because it's allowed to have a kind of regularization. We don't have the J equals 0 ambiguity. So yeah, and it's a natural length operator which upper when we do the computation, because in fact this comes from really the sig J symbol for the quantum group SU2. So it's really a formula that we have, and we didn't modify it. So.
But then when you do the limit, you recover the normal stuff.
Yeah.
J plus 1. So it's kind of consistent.
Yeah, when you do the limit, yeah. Q goes to 1. We recover the usual. We recover the normal cosine law, the Euclidean cosine law.
Any more questions? Antonino Marciano. I'll talk about cosmological constant and DSR scale.
Okay. Oh, where is the stick? It disappeared. Well, okay, I'll do without. Thank you very much. So I'm going to present a work in collaboration and inspired, thank you, by Giovanni, and in collaboration with Marco Matassa and Giacomo Rosati. So this is about the interplay of the cosmological constant with the DSR scale. We want to develop a model framework in which we can try to understand the phenomenology of bursts of particle coming from cosmological distances. So we need to insert another invariant scale here in the game, which is an expansion rate, a constant expansion rate of the universe. So we know from the talk of yesterday of Laurent that, I mean, if we have quantum effects and gravitational forces vanishing, but negligible, but whose ratio is non-negligible, we have a momentum scale which enter in the game. But what we want to do is to develop a theory in which laws are relativistic. So this is the play, I mean, of the game, the goal of the DSR theories. But then, I mean, we want to use this series, this model, in order to understand and to explain data coming from bursts of particle. So we need also curvature, because these bursts of particle experience curvature coming from these cosmological distances. And so, well, now, I mean, I'm going to skip this slide. We'll just say that this is just a historical slide. We'll just say that a first tentative of developing a theory with the three invariant scale, so the velocity of light and a momentum scale, which is the Planck scale, and the third scale, which is this constant expansion rate of the universe, has been worked out in a first approach, in a quantum groups-like approach, in an old paper by Giovanni Menino Gameria and collaborators, so among which me. And in that case, we derived some consequences in cosmology and astrophysics, and we developed a procedure of DSR slicing of Freeman-Robertson-Walker, which worked, of course, better than slicing Freeman-Robertson-Walker with the Minkowski space-time. So the idea is try to do something in a space-time with a constant curvature, so that we can approximate. We can make a better approximation to the universe. I mean, to a Freeman-Robertson-Walker model of expansion of the universe. And let me talk first about DSR relative locality in a flat space-time. So if we want to describe the propagation of particle in a theory in which there is an invariant scale, which is an invariant scale for the momentum, we can take the invariant of, let's consider here a 1+1 dimensional model. So very easy. So our particle, and I will consider massless particle, propagating only in one direction. Could be the radial direction in a 4-dimensional model. And actually, we can do that. So we'll just show the 1+1 dimensional model because it is easier. And so we have an invariant of an algebra that we can construct in which E and P are the generator of time translation and space translation. And we have a boost. Of course, we have only these three generators in 1+1 dimensional space-time. And this is the first invariant that is the invariant. So that means what we call the mass shell. I mean, we define the mass shell condition for a particle. If the mass is 0, this will be enforced to be 0 in a relativistic description of the word lines of massless particle. And you can see that these are the two terms that we can consider in order this to be the invariant of this algebra. So we have an alpha and a beta term. But look at that, these two terms here are actually the same at the 0 order, because for a massless particle, because now you cannot distinguish between the E cube and the E times p squared term. So, and what I'm going to show then is that we're going to find something, in this case, which is flat, which is that the physical velocity will depend on the sum of these two parameters. While this will be different in a curve scenario. So in order to derive what we have to derive, so the word lines that we need, we enforce a representation in terms of canonical variable in the phase space. So we pick a time coordinate and a space coordinate and a canonical phase space, and we represent the time and space translation and the boost in terms of this variable. And then, enforcing the covariant characterization of word lines, we derive our word lines that here is specialized directly to the case of mass 0. And you can see that we have a coordinate velocity, which depend on the inverse of our momentum scale. So now I'm going to show you some pictures since it's quite late, so I think that you will enjoy more seeing picture. So now if I want to describe what happened for a reference system for an observer which sits here, so at the origin of this grid, and sees two photons which are emitted. One with low energy, and the other one with the blue, hard photons. Hard means that we can see the correction which are multiplied by the inverse of the by inverse of the momentum scale. So what we can see here is that because of the slope of our word lines, which is this, because of the slope of our word lines, we have a different extension, a different velocity of the hard photon. And actually, an observer, which is a distance L, will see a time delay which is proportional to the inverse of the momentum scale times the energy of the hard photon, which is equal to its momentum. But this is not actually what the detectors see. What the detectors see, which is linked to the physical velocity, has to be recovered, making a non-trivial translation which uses the symmetries that we have introduced. So the physical velocity is what the detector, so the other observer, which is Bob here, sees. And actually, what we can see is that two things. So first of all, in the reference system of the observer, the emission of the two photons is no more coincident. And this is what is called relative locality. Then the other thing is that the time delay is quite different. Actually depends on alpha plus beta. There is no more this, but it's this. But it's still kind of remarkable, the fact that it depends on the sum of these two parameters. So we are not able to distinguish between the alpha contribution and the beta contribution. So now I'm going to show what happens if we construct a theory that this is important. This difference between the alpha and the beta contribution is important from a physical perspective, and this will be clear in a couple of slides. So now we want to do the same. For space-time with the curvature. So we introduce now another invariant scale, which is a constant expansion rate of the universe, and every observer should agree about the fact that the universe is expanding with a constant rate of expansion. So this is the zitter. And then they construct an invariant and an algebra associated, and they represent it in terms of conformal variables. So we have conformal time and the conjugated variable in our canonical phase space, and we derive our word line. See that the word line, factor out, the conformal factor it happens when we we study the emission of light rays. So in the standard case. And then we apply our translation, time translation, and space translation from one reference system to the other in order to obtain the same kind of word line. So this is the covariance that we have in our theory. So the word line has got the same form. But what happened is that the x0 and eta0 point where the word line crosses our axis now depends on the momentum of the photon. And it depends in such a way when we switch on the curvature, which distinguishes the roles of alpha and beta. And why this is important experimentally? Well, I'm going to show you that, well, first of all, I mean, the relative locality side of the story works in the same way. We have to go from one observer from Ali's point of view to the Bob point of view through this non-trivial translation. But now we can distinguish the difference, physical difference, in the time delay detected by Bob, considering two sets of value for alpha plus beta with the same sum into for third. And you can see that more closer is alpha to 0, wider become this time delay. And why this is important? This is important because now if we try to fit, yeah, thank you. If we try to fit the data, if we plot the time delay that we would have, depending on the value of alpha and beta, setting the time delay to agree for the gamma ray burst 090510 that detected at Fermi at 0.9 redshift, you see that for alpha equals 0, the time delay grows faster, while for alpha different than 0, non-vanishing, you have a different time delay always. Alpha equals 0 is the time delay which is predicted by, in a universe which is expanding with a constant rate, is the time delay which is predicted by a Lorentz symmetry breaking scenario. While for alpha different than 0, you have the the relativistic point of view of the theory. So this means that if you want to put constraint from data from z very small, you will not experience the difference between alpha and beta. Indeed, I mean, what you can see that for small z, for instance, if you pick up the PKS 2155 from Hertz, so you see that the bound on alpha and beta are more or less the same. But if you go toward the higher redshift, so you experience much more the curvature of space-time, you see that you can arrive to Planck scale sensitivity even for beta.
Are you assuming a constant Hubble?
Yeah, that's right. So a constant Hubble is a better approximation for this z, not for the other one. So this is the first point. I mean, of course, I mean, we have to develop with the model for Freeman, Robertson, Walker this strategy. But this approximation with de Sitter slices, it's much better than the one that you can do with Minkowski slices.
Why?
Well, because the why is explained in the first paper with Giovanni about de Sitter, de Sitter, sorry. We did we showed that even at the classical level, the differences that you have just to show a very easy fact. If you want to discretize in steps, if you want to discretize, the chalk here.
It's indeed obvious in a sense. I mean, the rate of expansion changes rather slowly by our scales.
So if you want
to observe a nearby source, it's going to feel like you are in the Sitter roughly, not like you're in Minkowski. I mean, the first correction is the Sitter. And then if you have better sensitivity, it's going to feel like, am I wrong? I don't know. I'm wrong.
No, I mean that's no, but I mean, well,
then we have to
no, but if you,
people on that.
I think the only degrees of freedom that you have, I mean, in the metric, which is the conformal factor. So this is the approximation that you have with Minkowski, and this is the one that you have with the Sitter. So which is closer? I mean, it's the Sitter is closer.
Is the Sitter Minkowski
The Sitter is closer.
Is the Sitter or Minkowski better approximation?
Well, we have done the calculation. It's another seminar. But actually, we have the calculation, but we never publicize it because it feels to us it's obvious.
It's not obvious.
But we have the...
It's obvious to you.
It's the concept. The rate of expansion changes very slowly. With respect to the scale of...
Okay, let's put it this way. The acceleration in one case is positive, in the other case is negative. It's completely different.
What?
I mean, for example, if you have a Freeman universe without a lambda, it accelerates with a constant.
Well, but if you have a Minkowski space-time, it's just static.
Yeah, but that's
flat.
The point, is it? Depends on what you're computing. I mean, that's the thing.
Well, if you want to compute, if you want to take into account the time delay of gamma ray burst, I mean, and you're not considering any effect of curvature because you're considering Minkowski space-time. You just think, I mean, you're not considering any kind of, interplane that it could be between curvature and Planck length effect. While in the other case, at least, I mean, you're trying to do it. It could be wrong, but you have a model.
It could be very wrong.
All right, let's continue on.
Well, okay. Well, I just arrived. So this was my last slide. So it's, of course, I mean, it's to make these steps more rigorous, we have to go toward Riemann-Robertson-Walker. So this is a step forward. But the other thing is that if once we arrive to develop the strategy for Riemann-Robertson-Walker, and we agree about that, we can actually think also to mimic what we have in varying speed of light theories. Because somehow we can think that speed of photon, depending on energy, mimic in an effective way the varying speed of light if we think that the thermal energy of the universe, I mean, is different at various epochs, and so we will have, I mean, different characteristic energy of these photons. Okay, so that's all. Thank you.
Sorry, what is the physical mechanism that breaks the degeneracy between alpha and beta?
Is the fact that you're introducing
redshift.
Yeah, is
E and P are no longer. Well, I have a comment.
You want?
Can I?
No.
You correct. I mean, just a comment, which is that there are previous papers with algebras with 3 invariant scales.
Yeah, I mean there is the paper Jurek and Lee did.
This is the first time that somebody works out word lines. So.
Jurek did it. Yes, Jurek and Lee did it, but I didn't write there. But I mean I was mentioning a theory with 3 invariants of word lines. This has been. But of course, yes. I mean, triple special relativity, 2004.
We don't mind.
Okay.
I don't mind.
Since you were so gracious, not to look at it.
Any more questions? Comments?
Okay.
I guess. So I really forget. So I want to basically understand what's happening. So the point is that is that formula on top there. Alpha and beta appear in different terms, but I mean, if the lowest order E is the same as P, then you would just get alpha plus beta. But then somehow you're saying that in an expanding universe, it's E is not the same as P.
No. I mean, first order. I mean, well, actually, I mean, the first thing is that if you look at the expression of E in terms of phase spacing, this is no more true because I mean, there is H, which messes things. And also, the second point is that even if it were true, I mean, the mass Casimir is what it was telling you that E is equal to P, okay?
Yeah.
But the mass Casimir now has not H there.
But that's like a tiny direction.
Okay, and then the second point is that even if it were true, they appear in different combination.
Yeah. Okay. So that's very comprehensive because you would think that like the energies you're talking about are much larger than Hubble scale, so H should be negligible. In that relationship. But you're saying.
But it's the dependence on the redshift, which is different. I mean, the way in which H enter is the same. Is what makes a difference is the dependence on the redshift, not on H.
Yeah.
Rob, last question from Rob.
A strange thing, which probably the effect is negligible, is the Hubble diagram. So basically, we have luminosity distance on one side, or on the other side we have redshift, or anything which is, for example, angular distance, all that stuff. Would that be modified very much in this kind of situation?
I don't know.
Well, it's interesting.
Well, the effect probably is small, right? Because
Well, but it may be something that can put limits. I mean, small is interesting. You should explain to us what's the proposal.
Okay, I'll explain to you.
All right. All right. A quick question. This is a quick question.
Can you say what is the relation between the symbols that you write in the blackboard and the things that we measure? H. How do these things relate to the things that we measure?
So what we measure is no, but we measure also the momentum of a particle.
But we measure.
So you're interested to know what we measure?
No, let me say something. We measure momentum of something using a calorimeter. We have heard how you get the energy of a high energy cosmic ray by adding up the energies of the particles that come out. But in your schemes, the energy is not additive. So this energy that I measure using a calorimeter has nothing to do with this energy that you have.
What we measure are the conserved quantity in this scheme.
So how is that related to the energy that I measure in the...
Since it is a relativistic theory, we have another way of understanding what is happening around. We have introduced two symbols which are E and P, and the Poisson bracket with the Hamiltonian constraint at 0. That means that E is conserved and P are conserved.
But conserved in what sense? You need to add the energies of the different particles to compute the total energy. What's your conservation law? When two particles collide, is energy conserved, meaning the sum of the energies, or is this coproduct which involves some more complicated process, which also depends on the order?
Daniel, you probably don't know that in the most studied coproducts, energy is linearly additive. It's just the spatial part, which has some.
Well, you have one energy that is linearly additive, and there is another energy that is not linearly additive.
Okay, so this sounds like something that should definitely be continued on later to the night over some beer. Now we have Ivan Arraut from Fudan University, who's talking about dark matter and dark energy as a possible manifestation of fundamental scale.
Thank you. You can.
Screen up. Somebody's going to.
What do you mean?
There are people watching us.
So.
Yes.
So my name. Do you understand it? My name is Ivan Arraut. from Osaka University. I'm a PhD student, second year. I will talk about the possibility of obtaining dark matter and dark energy as a possible manifestation of fundamental scale. Basically, my project is divided in this moment in three parts. The first part is non-local gravity and scalar and tensor models in order to analyze the same problem. In this part, I am receiving the collaboration of Professor Misao Sasaki from Kyoto University. The second part is particle creation by black holes. In the Q-Barman-Fogg formalins, it seems to be trivial, but it's not so trivial because it seems that the Bogolubov transformations, the standard Bogolubov transformations are not valid anymore when you introduce the Q parameter deformation. I was analyzing that actually 1 week ago with Professor Kempf, who accepted to collaborate me in this part, Akin Kempf, who is in University of Waterloo. And the third part is what I will explain here. So basically, my motivation is the following. Why is lambda, why is the cosmological constant so small? I want to explain also the galaxy rotation curve and gravitational, the observation of gravitational lenses. And it seems curious for me why lambda appears as a fit parameter for the galaxy rotation curve in the Mond modified Newtonian dynamics formulation obtained by Milgrom. So that's it. Basically, the fit parameter in Mond is, I will introduce like this, 26 meters. And as a consequence, you have the Tolley-Fisher relation, which is this. Basically, this is experimental. The Tolley-Fisher relation was derived experimentally, and it seems that modified Newtonian dynamics agree with that. For the first problem, which is the cosmological constant, it seems in agreement with some authors, but from the 0-point quantum fluctuations, the appropriate cutoff seems to be a geometrical average between, for the density.
Isn't that with the luminosity?
Yeah. But after you can get a relation between mass and luminosity, and you obtain something like that. It's written in the paper, in some papers. So for the cosmological constant problem, it seems that the appropriate cutoff is this. Obviously, it's too large for being a cutoff, but there is a possibility that there is some cancellation between modes, between infrared and ultraviolet modes, such that in some sense, the relevant term, the final relevant term is this. The essential philosophy of this, which I have in mind, is the following. It seems that the screening of the cosmological constant, and this is not the only approximation that maybe suggests the same, it seems that the small value of the cosmological constant, I believe that is associated with the existence of dark matter. Is the ansatz. So let's see what happens. First, let's analyze. On formalins, where I introduced two scales, the Planck scale and the cosmological constant scale. Inside the Q-Barman-Fogg formalins, which was worked by, in principle the quantum groups were worked by Sham Majid and other authors, but also Akin Kempf did something with the Q-Barman-Fogg algebras, and he obtained, after deforming the bosonic algebra and so on, an expression for the generalized uncertainty principle given by I think that this is given by this. This is Q. Well, this is the ultraviolet, the familiar ultraviolet cutoff. This is the infrared cutoff. So if we impose as an ultraviolet cutoff the Planck scalar ultraviolet cutoff, the Planck scale, as an infrared cutoff, the cosmological constant scale, then Q is approximately given by this value, which is the form parameter. Additionally, there is a relation between both scales, which is, this is not new, this is already done by Professor Kempf in some of the previous papers, of his previous papers. So what he did in such a moment was to obtain a minimal scaling position and a minimal scaling momentum. How did he do that? He defined a function
excuse me, I'm trying to follow your notation there. So you have L Planck, you have R lambda, and then there you have some cutoffs there which are different.
This K and L are related. Actually, I should have written that, but yeah, if you replace Q by this value and you replace Q here, you can obtain the values of K and L, I think. I mean, basically, you have two free parameters in this theory, in this model or whatever, and I impose the two free, which are these, a large scale and a small scale. So let's see. If you define this function, you can obtain the minimal scaling position if you evaluate this and impose this. This is what Kempf did. You obtain this. Analogously, you can obtain the minimal scaling momentum. But additionally, I added as a third condition, which was not done by Kempf, but I added as a necessity of comparison with black hole thermodynamics at the beginning. But and that I define as the total differential of this as I send this to 0 and additionally impose the total derivative equals 0, and I obtain the general extremal condition is infrared ultraviolet mix. So this basically is an example where a theory which two scales differing one from each other provides an intermediate scale as an extremal condition. So this is the geometric average between the Planck scale and R lambda. So if you analyze, for example, obviously maybe it's quite different, but if you analyze, for example, the case of Mont, actually that's the appropriate cutoff for the cosmological. If you want to obtain the vacuum energy for 0-point quantum fluctuations, because basically, yeah.
I guess I'm not understanding.
Yeah.
These uncertainties are postulated, are they derived from some commutation relations like they are normally derived in quantum mechanics? Or should we change all the way we...
Originally, the origin of this is the Q-Warman-Fock formulas, and you have a deformation of the bosonic algebra. So you define the standard way, the operator in position, the operator in momentum, with its appropriate parameters, and you apply the commutation relations, and you obtain such relation.
So, so you change the algebra of the Heisenberg.
Yeah.
Also, the Poincaré algebra has changed.
I am not sure. I will check that point. But that's anyway. If we make a plot, well, okay. Anyway, the opposite. You have something like this. If you plot, the plot of that expression for generalized uncertainty principle is something like this. This is the Planck scale. This is 1 divided by Planck. This is R lambda. This is 1 R lambda. This is in the analogy with black holes. It is, oh my God. Okay, it's too slow. Anyway, I will make a resume. So the coherence region is this. This is the coherence region. And after you can wonder yourself, okay, what happened, for example, with dark matter in Mond? Modified Newtonian dynamics is a theory in which postulates a fundamental scale, which is A0. It says that when the accelerations are of the order of this, there is a correction for the dynamics operating in the galaxy. Basically, if you have some, I mean, this is the total acceleration in the pure Mondian regime. You have this, which in the case of circular orbit would be like when equality with the standard Newtonian case, you obtain, of course, the Tully-Fisher law. There is a problem. There are some problems with Mond. First, it's not a relativistic theory, so it cannot predict the gravitational lenses. It doesn't preserve the conservation of momentum. That's why people try to do relativistic formulations, like, for example, Bekenstein and others. And it doesn't have a limit for the scale at which, I mean, if you analyze the galaxy rotation curve, velocity and distance, there is no limit for, I mean, the curve never decreases. But that's not a problem. Actually, that's a local effect of the cosmological constant, and I will explain briefly why. That's one of the lessons of cosmological constant. 0? 1 minute, oh my God. Okay. One of the lessons is simply, if you analyze the standard case of cosmological constant, let's assume in vacuum, whatever, when you have the metric, this is dt square. This, the G0, the air, when you apply this, you obtain a scale which is very, very important. This scale is basically the scale at which the attractive and repulsive effects cancel. And this scale marks the limit, the extension of the galaxy rotation curve. If you add this term here, it's something proportional to something like this, and you obtain that at that distance the velocity basically goes to 0, and it marks a limit for the galaxy rotation curve. It can be seen in the effective potential, for example, when you analyze the effective potential. Is finished? Okay. Just 1 second. I mean, the effective potential, you have, this is the stable orbit, and this is the scale which I am talking about. This scale is not new. This is used by Boso-Hawking, for example, for defining the black hole thermodynamics for spatial de Sitter space. They look the static observer basically is in this position in this spatial de Sitter space. So that's not new. The conclusion is, well, for concluding, the conclusion is simply, I want to extend these ideas of deforming the generalized uncertainty principle and the algebra and the bosonic algebra to the gauge gravity, like Yang-Mills gravity and so on, and see the consequences. And it seems that the possibility of infrared ultraviolet mixed effects can provide some evidence for dark matter. And that's all. Unfortunately, the time is over. Okay.
Just went over. We have time for one question.
But you need a positive or negative cosmological cost?
Positive.
Usually, usually it's negative in this. In this type of method, isn't that true? In your case, it's
no. It depends of the signature which you use for. It depends on the signature. So, does it? Yeah, it's positive.
Maybe I can ask while that's setting.
Yeah.
So, I think I missed the main point. I didn't quite get. You're trying to relate the dark matter to the cosmological constant somehow. Is that right? So can you just say in a sentence what is the relation that you found, or that you're?
Well, basically, the scales at which the dark matter happens are the geometric average between the gravitational radius and the overall scale. That's what
Gravitational radius.
GM. That's the Mond regime, basically. So extending the analogy which I did for.
You should wait.
I mean, when you modify the gauge principle in Yang-Mills theory, it's possible perhaps to obtain the dark matter effects from. I mean, that's the scale which I want to obtain in order to analyze.
You want this geometrical average to come out somehow from
It's in my pocket.
Yeah.
What does that have to do with modified uncertainty?
Well, because the uncertainty principle gives me some analogy from what I want to do from the case of it's some kind of analogy. I was explaining if you have two scale theory, what can happen? You can obtain an external condition in which a third scale appears, which is the geometric average of the.
But it's not the same physics. It's just an analogy.
No, that's an analogy. That part is an analogy. It's not the same. Fortunately, the time.
So we're gonna have. I know we all want to remain and continue talking here. But we have Alejandro Satz from the University of Maryland.
Oh.
Who's going to talk about quantum gravity.
This is actually like. Yeah. Okay. So thanks to everyone who stayed till this late hour to hear me talk. I promise I will keep it brief in the interest of sanity. So yeah, I'll be talking about quantum gravity for cosmology in the mini superspace approximation. This work I've done with Daniel Littim at the University of Sussex during a research visit. So the outline of the talk, is I will give a very brief introduction to the formalism I will use, the Renormalization group in the mini-superspace approximation. I will explain very quickly how the RG flow equations for the gravitational coupling and the cosmological constant are derived, and show how is the flow diagram for the system, and in particular its fixed points and this new feature, which is the limit cycle. I will explain then how you can interpolate between a regime with and without a limit cycle, and what implications this has for the problem of cosmological fine-tuning. What we want to consider is basically the simplest possible system that can still be called gravity, which is the whole universe, in the approximation of the spatially flat Friedmann-Robertson-Walker metrics, which I write in this form, in which the conformal form, so T is the conformal time, not the usual time, and the mini-superspace action that we use is this one, where V is the spatial volume that we have integrated over, and A is that conformal scale factor. And we want to study quantum theory through the tools of the exact renormalization group, the same tools that are used in the asymptotic safety research for quantum gravity. So this is the line of research that we've heard before today from Daniel and maybe from others. And so the basic idea is to introduce a mode cutoff, like an IR cutoff function RK, and the partition function is in general for a scalar field, but the same thing is for gravity. This leads to a flow equation for the effective action gamma k that then can be computed within a certain approximation, or rather truncation, in which you just select certain terms and study their flow and the beta functions. So there are already many existing results for different ansatces for the form of gamma k. The main ones for my purposes are the one in which gamma k has the form of the Einstein-Hilbert action, and the one in which it is an approximation to Einstein-Hilbert action, in which the only degree of freedom is a conformal factor, chi, which relates it to a fixed reference metric, g hat. In that particular theory, the action is this, where r hat is the Ricci scalar for the reference metric, and then you promote these lambda and this g to k-dependent couplings, and you find the flow with this flow equation. So if you see, this is very similar to this. If you take as a reference metric a flat space, and you stipulate that chi can only depend on time. We are in the Euclidean regime, by the way, not in proper cosmology, but in Euclidean cosmology, if you want. So what we're going to do to derive the beta functions is just follow the calculation that has been done in previous research on this theory, and just kill all the spatial fluctuations and leaving only fluctuations that depend on the temporal coordinate. So
what is that box, funny box?
Yeah, it appeared badly for some reason, but it's a box with a hat on top, which means the D'Alembertian of the reference metric. So if you see in this case, in which the reference metric is flat space, it will be just the usual flat D'Alembertian, which in this case means it is dt squared. So okay. Okay, so the procedure that we use is that when you actually put this kind of, this kind of action into this flow equation and compute this thing, you get some traces, which are integrals over momentum space, to compute these beta functions. And what we do is that, so formally, at a very schematic level, what you have is that the beta function of the gravitational constant is some integral momentum space of some function of p squared and k, and similar for lambda k. And what we do is simply to introduce a delta function that will kill all the fluctuations in as many dimensions as we want. In particular, in the case n equal 1, we are killing fluctuations in three dimensions and leaving only one of them. So this is the case we're interested in.
Aren't you just doing quantum mechanics now?
Yes, yes. It's a kind of quantum mechanics theory. Yes.
So you're computing beta functions for quantum mechanics?
Yes, this has been done. So when you do this, you get flow equations for the dimensionless versions of the couplings, like the dimensionless g and lambda, which take this form in terms of the eta, the parameter eta, which is what is usually called wait, I got a mental lacuna here. The anomalous dimension for Newton's constant. They are very similar to of course, to the flow equations for the full theory for the conformal factor depending on 4 dimensions. And the only difference is that this parameter n appears here and is 4 for the full theory and 1 in the theory that we're interested in, the mini-superspace theory. So we are studying like a kind of approximation to a theory in which you kill off some of the fluctuations to study a super simple case in which everything is homogeneous by fiat, if you want. And we find that it just can be expressed as a tweaked version of the original theory with a different numerical parameter here. And I should say also that there is something missing here, which is that all these equations have a scaling factor for the Newton's constant, which is 3, which is related to the fact that here you have this spatial volume. Oops. Here you have this spatial factor that you have integrated over, and that you can absorb it into G, and nothing depends on the value of that. Okay. So here I compare the flow that I find for the full theory in which the conformal factor depends in 4 dimensions, and for the truncated mini-superspace theory. This flow is very similar to the ones that Daniel was presenting earlier today for the full Einstein-Hilbert theory. Like it's basically qualitatively the same thing. In both cases, we have a UV attractive non-Gaussian fixed point that is like the high K like limit of the flow located at positive G and lambda. In both cases, we have a Gaussian fixed point B. In both cases, there is a singularity in the flow at lambda equal 1/2, which is an artifact of the kind of truncation we're using. In both cases, there's a degenerate fixed point at the point where this singularity meets G equals 0, this point C, of which Daniel was talking a lot earlier today. And in both cases, there is an IRN attractor at lambda minus infinity G equals 0. But the key difference, as you can see, is that in the mini-superspace case, the flow leaving towards the IR, all these arrows point towards the IR, like from the UV to the IR. The flow leaving the fixed point and flowing towards the IR gets stuck in this limit cycle, like, and does not reach like the semi-classical regime, which is this region next to the Gaussian fixed point. So it's a qualitatively new kind of behavior, and it's like really interesting, despite the fact that it appears in such a simple like version of the theory, or perhaps because of that. And we certainly should study a bit more what is going on there. So
there's this fixed point in the truncated theory on that softening factor that you have in the integral.
Sorry? The RK, the cutoff. Yeah. So this is for a particular version of the cutoff, which is the one most commonly used, is the optimized cutoff. I really haven't studied other like cutoffs to see how it works. I really haven't studied that. I doubt that typically doesn't change the qualitative features of the flow. Like, so I doubt it will change a lot, but I honestly haven't done the calculation. Like, but generally, like, it can change this kind of qualitative like behavior. So okay. So one thing in particular that we can study, since we have this parameter n that was introduced as a number of dimensions in which we like scale fluctuations, but we can certainly study the theory for continuous values of n. Like because we have the equations that are defined for any value of n. And so we can study what happens when we start increasing n, like slowly between this and this. And what happens is that the limit cycle increases in size, like gets larger and larger, like until at a particular value of n, it collides with these fixed points that are sitting down there in a kind of degenerate limit cycle. And this occurs at what we call the critical value of n, which is 1.47 more or less. And so this is like a bifurcation event, if you want. And in this particular value of n, all the trajectories that leave the fixed point towards the IR will eventually go towards this like limit cycle and approach this trajectory that goes between the degenerate fixed point and the Gaussian fixed point and back and forth. Like, and if you keep increasing more, and then you are suddenly, again, in this kind of regime, and the limit cycle has disappeared. And how this happens exactly is that when you increase the value of n towards this, the period of the limit cycle, like the time it takes it to cycle around, measured in RG group time, so log k, increases logarithmically and diverges, which is what you expect because you are getting arbitrarily close to fixed points. Okay, so and the theory at this particular value of the critical point of the critical at this particular critical value of the n parameter has this very interesting feature, like it has potential implications for cosmology, which is what I will discuss now, which has to do with the semiclassic, for the possibility of a semiclassical regime. In general, within the asymptotic safety research program, if you want to have like a good cosmology, a semiclassical cosmology, like with a good like a low energy physics that matches what we see, you need that there's a problem there that should be lambda k there. You need that the physical values of lambda k and gk remain approximately constant and also small and positive, or the wide range of scales in which you measure them, like from the Earth to cosmology. And this means in practice that the RG trajectory that is followed, like by reality, should spend a large amount of RG time, so a large amount of scales, like very close to this point where the values of g and lambda are small. So not any trajectory leading from the UV fixed point will satisfy this. You have to have a very particular one that gets very close to there before being pulled away in this direction. So this is like the fine-tuning of the initial conditions, like problem. And this happens for the full Einstein-Hilbert theory and for the other like wider truncations have been studied, and also in the municipal case, we have seen that, well, like things that trajectories that leaving from here do not get near this point, but also there are like fine-tuning trajectories that leave, in this case, from this singularity, and there has to be only particular ones that pass very close to here. However, in this particular case of the critical value of the n parameter, we have that any trajectory leaving from the UV fixed point is eventually fated to be arbitrarily close to the Gaussian fixed point and pass an arbitrarily long amount of time next to it. So this is a kind of way in which the problem of the fine-tuning of the initial conditions resolves itself, like within this particular approximation to the gravitational renormalization group applied to cosmology. So I certainly don't want to claim that this describes reality, like it's a super simplified model, like and besides it's a value of n that I don't know how it represents anything physical. Though curiously enough, there are these studies of discrete quantum gravity, like in CDTs or EDTs actually, because this is Euclidean dynamical triangulations, in which you get effective dimensionality of space-time, which is not very far away from this. So that might be a potential connection. But still, it is very interesting that this kind of behavior exists in a version of the gravitational theory, which is not so far away from the one that exists in reality, and that maybe it could be achieved with a more complicated truncation. So going to the summary and repeating more or less what I already said, we have studied the mini superspace reduction of the Einstein-Hilbert gravity, and we have computed beta functions for g and lambda. We see that it has a limit cycle. That is a novel feature of this that does not appear in the full theory, and that we can study how this limit cycle changes with this parameter n, which measures in how many dimensions we truncate we suppress the fluctuations of the conformal factor. And we find that there is a critical value of this tuning parameter at which the period diverges, and then it disappears and goes away, and the period resembles the one that we know from higher values of n. And at this particular value of the critical of the tuning parameter, we have a new possibility open for having a good cosmology without needing of fine-tuning the initial conditions of the renormalization group. I think that's all.
I have a couple of questions. First, do people know of other examples where you get limit cycles in the RG flow? or is this? So that's.
Yeah, he can answer that question. Like,
yes, we found this exactly another limit cycle with the RG flow in a similar model, in a similar approximation, which is the conformally reduced Einstein gravity. But I personally don't believe that one should take it seriously, because if you project on a flat space-time instead of spheres, that's what they did, the limiting cycle is not there anymore. So it's possible to find this type of behavior, but I don't believe they are real.
But aside from these, no examples are known where you have limit cycles.
For instance, in exact, in the full-fledged Einstein-Hilbert theory, but using the spin connection of, the Stephon rather than the metric as the fundamental variable, we also discover the limit cycle. And
how about in flat space? I was thinking more of just flat space quantum field.
So there's been a lot of discussion recently in the literature about the existence of such theories in perturbative regimes, and it has been shown that they are associated to theories which are scale invariant but not conformal invariant. And it's something that people believe that cannot exist. But now there seem to be examples also in 4 dimensions, but they look pretty contrived. You have to go up to 3 loops to see the 16.
Isn't the animal effect explained by a limit cycle of the RG flow?
Yes, it's a one parameter limit cycle.
It's a different, no, it's a different.
But then
That's different
there's a scale invariance which is approximating the relevant physical system for which these sort of things have been observed. The log periodicity of the spectrum and so on, but that is approximate, of course. If you go deep enough into the nucleus, you would find something that is not scale invariant anymore.
These people claim that they find it different from
the second.
Okay.
Well, let me ask the second question. Which is, and since this is really quantum mechanics, you might think it's possible to understand everything perfectly in some other way, you know.
I don't think it's quantum mechanics.
What?
I don't think it's quantum mechanics.
Well, it's one. I thought it was agreed. Alejandro thought it was quantum mechanics.
Yeah, in the sense that it is just a variable that depends on time, right, and not on like that's the degree of freedom, right?
It's zero
A of t.
one-dimensional.
So
I'm just wondering if there's another way of seeing all this or analyzing these things, just using the Schrödinger. I don't know what exactly, but since people understand quantum systems extremely well, quantum mechanics systems, can some of that be applied here?
yeah, there probably should be another way of finding this, like if it is real and not an artifact. That's true. Like, but I.
Just extensions, maybe.
Mm-hmm.
So I guess maybe the devil's advocate, maybe too harsh, but the devil's advocate point of view would be that, first of all, so the fact that in quantum mechanics, when you start solving a Schrödinger equation, you don't get limit cycles, at least for this particular system, that says that there's something wrong with this ERG framework, because that doesn't give you, we know the exact quantum mechanics how it works, and when you solve it, you don't get it. But then you get it here. So, but I guess back to Raphael's point is that there is a C theorem that prevents existence of limit cycles in the renormalization group. So systems that satisfy C theorem that have run this. Yeah.
Okay.
I would like to answer to your point and make a general comment. There is a very important paper, I would say seminal paper by Ken Wilson in 1974, before the discovery of asymptotic freedom, where he discusses all possible behavior of beta function at very high energies. And there is one long paragraph on the possibility of having a limited cycle in QCD, and also to observe that, because then what you will see that the cross section will oscillate as a function of the transverse momentum.
Mm-hmm.
So it was very clear to Ken Wilson that there is nothing which will prevent, in general, a behavior like that from the renormalization group. Just that asymptotic freedom came a couple of years after, then everybody forget about that. But in principle, I will not be, it's not impossible. And it's a very nice paper. I think it's very useful to read that.
And the related remark is there is a substitute for the C theorem for our kind of flow equation, which in a certain sense holds or has implications similar to the C theorem in 2 dimensions, but in the case of gravity or gauge theories where you need ghosts and you have you always saw these super traces rather than traces in front of the operates on the right hand side. In all those cases, it does not predict or it excludes a gradient flow, and so that is in principle consistent with the limit cycle. In principle, one could have that, but the point is this
approximation.
This theory, this Gray, which has been worked out by a student of mine. This is the, so to speak, the mother theory of this reduced quantum mechanics system, and this better approximation does not show any limit cycle. And so if you go to this worse approximation and you get one, then in this case it's clearly...
It was already in your data, in your number, in your data, we all get that.
Clearly, it is a nice toy model, but it cannot be lifted to the level where
of cosmology or things like that.
Where to judge consistency with the C-like theorem.
Okay, so last question.
I'd like to make statements. I mean, clearly the C theorem doesn't require this theory simply because it's an Euclidean one.
Because it's a
Euclidean theory.
But I mean, it's supposed to approximate the real universe, right?
No, but I mean, it's a Euclidean computation, and referring to a theorem which constructed from the cosmic space-time and whose proof uses crucial elements.
No, that's not. You can apply even Euclidean. I mean, there is this paper by Morris, it's completely Euclidean. And then if you have a gradient flow, then it's impossible.
Yes, but obviously this is not a gradient
That's
flow.
not the answer, Daniel.
Yes. So obviously this is not a gradient flow. And the second comment concerns the comment by Martin, which is the question as to whether this is better or worse of what has been studied previously. I mean, there's an element in this study which we deliberately enter, which is the following. We often see in quantum gravity studies that the high energy regime displays a dimensional reduction. This is seen in lattice simulations. This is seen in these RG computations controlled by the anomalous dimension, which is carrying this effect, and even in other studies which use different conceptual frameworks. Okay. One element we wanted